Annyeonghaseyo. Welcome back to Automatic Control Systems lecture. I am Kalyana Velvolu with the School of Electronics Engineering. So, this is the last part of Automatic Control Systems. We almost reached the end of Automatic Control Systems lecture. So, this is week 14 part 3. In this lecture, we will be reviewing the important aspects of what we learned in the second part after the midterm. And also I would like to discuss with you about learning aspects from now on and how can you improve your control systems knowledge. So, the outline will be, first we will be going through the overview of control analysis and design. I would like to brief you about root locus, PID controller and frequency domain and its advantages of how we can actually solve wide variety of problems. Next, I will also shortly discuss about controller implementation, because once you design a controller you need to implement. So, we have various tools, the software tools that are available. So, we can actually use some controller implementation. We will discuss about them, and last I will give you some suggestions on the structure for the final exam. So, what we learned in this class is, initially we learned modeling, then we learned about time domain analysis, then we moved on to steady state stability, steady state analysis, and then we learned about root locus, and then from root locus we moved to PID and then to frequency domain. So, if we combine everything, what is that? So, what we learned is to actually develop a controller that can improve the performance. So, the performance, now what you understand is about error dynamics or something specific requirements like damping ratio or omega n, or they are try to relate it to time domain specification like rise time, settling time, etc. So, all is related to the output. So, then we also learned about the importance of feedback. So, once we make a feedback control system, then we can actually develop the controller. So, when I say controller, I am not saying PID controller. We have several ways of designing a controller. So, before we go into how we design that, so what are the aspects? What we are doing is, in this lecture is, when you have a system, we try to model it as a standard second order system, right. So, in this lecture our analysis is limited to standard second order systems. Any model which we develop, we are going to model as standard second order system. So, once we model that, we are trying to include a controller such that we modify the closed loop performance. So, we can modify the control system, we can modify the closed loop transfer function, means when I modify the closed loop system, we modify the characteristic equation. So, when I modify the characteristic equation, I change the location of roots. So, the most important is, when you change the location of the roots to a new location, we change the properties of the system. Properties like eta, omega n, they change. So, we try to change to satisfy certain requirements. So, the most important in control is the requirements. So, get the requirements, the error requirements, steady state requirements, any requirements, model them in terms of system parameters, and then try to design the controller so that you can satisfy the requirements. So, we have a requirement, and then based on the performance we try to achieve the requirement. So, this is the aspect, and this is what we learned earlier. Now, this can be achieved in several ways. The several ways are, first, one of the design technique is root locus. So, root locus is not only a design technique, but also analysis technique. So, if we understand correctly, we can use root locus to actually analyze how the roots change with the change of gain. So, you have a gain here. So, if you compare now with our controller to this transfer function, here k is like a controller. So, when you change k, the closed loop transfer function changes, the roots change, properties change. So, selecting a k, you can actually visualize, you can actually foresee what changes the system can. Root locus is a nice technique because you can see every change in the root locus plot. You can see every change in the root locus plot if you actually know the k. So, by plotting the root locus, we can actually analyze the system behavior, we can analyze the system stability, and then we can select a gain to choose the location that satisfies the specification or the requirements. There is one more thing you can do. So, the other thing you can do is, we learned that if we add poles and zeros, we can modify the root locus. So, if the system root locus is not really good and you want to slightly modify, you can add a pole and zero at the controller. So, not only k, you can slightly modify by including a pole and a zero. You can add a pole or a zero, you can slightly modify or improve the stability, decrease the stability. You can know all these aspects from root locus. That is the main advantage of root locus. When I add a pole and zero, I can actually see how the root locus changes, and then I will be able to better design the system. Now, the other thing, if you look at this root locus structure, first thing that comes to me is a P controller. So, the P controller is exactly the structure. So, with a simple P controller, this is what we have. But then P controller, we can only satisfy one requirement. But however, the other advantage in the root locus is the visual. So, you can actually see how the root locus change and how the system behavior will be modified. And if you add poles and zeros, this design is even much better than P controller sometimes. So, root locus has its own advantages. First time when students learn, it will be not so direct to understand the importance of root locus. Most students perceive this one as just a graphical tool, but to me, I see it as a design tool, a good design tool. That is another main important aspect of root locus. So, not only drawing the root locus, but we can design a better closed loop transfer function. I can select a pole, I can select a zero, add a pole or a zero, and modify the behavior. So, that is one aspect that actually separates from other design, because if you use root locus, you can see directly how the roots change, how the location changes, and how the properties change. Now, since we discussed on root locus, we can compare with the PID controller. So, what is that advantage in the root locus and what is the advantage with the PID controller? As discussed earlier, it has its own advantages, but then not all can be done. We can improve the system closed loop behavior, but you can't change some of the aspects. So, some of the aspects that you can handle with the PID controller are special. So, what we see in a PID controller is a much robust controller, and what we see is it has three terms: proportional term, derivative term, and integral term. So, if you look at a PID controller, it can have any combination: a P controller, PD controller, PI controller, PID controller. Then this is one of the most popular controller design techniques employed even today in industries. And this is the first choice controller to solve many problems. Nowadays, we have many advanced controllers like fuzzy controllers, neural network controllers, artificial intelligence controllers. However, still many companies just use what we call traditional PID controller. The first step for any control student to actually design is to develop a simple PID controller. So, that is why it is one of the most popular controller. Now, coming to what PID can do is, P can actually have its own advantage, which we can directly see in the root locus. Then we choose a PD controller. When we compare a P and a PD, P controller can only influence either one of the parameters in our standard second order system. So, if we look at our standard second order system characteristic equation, P controller can only influence one of the parameters, only one. So, either can improve damping or improve natural frequency, the other will decrease. Then we try to choose a PD controller. A PD controller can actually independently select eta and omega, can slightly improve the performance, can give you speed as well as also provide good damping, its own advantage. Then P and PID has some kind of purpose, and then what we see in a PI controller is it improves the steady state performance. As a PI controller introduces a new pole, it increases the type of the system. So, when it increases the type, it can improve the steady state error performance. So, and then most common controller, most robust are the combination PID. As I told you, everyone calls it a PID controller, they do not call P controller, PI controller, PD. Common way is they just say it is a PID controller. It is up to you to choose whether you want KP, K term, KID, KI term, KD term or KP term. So, the other advantage of a integral controller is it can also overcome the disturbance. So, the good thing of the PID controller is it can satisfy all the requirements, time domain specifications, and can also overcome the disturbances. Moreover that it can also provide stable control performance. So, that is one of the reasons why PID controller still remains as one of the most popular control technique. So, comparing root locus and PID, both has its own advantages, but comparing, most people like PID controller because a lot of time the specifications, the requirements are time domain. So, they give us the eta, omega n or the steady state error regulation. So, all these requirements can be easily handled with one of these parameters. However, if you do not like the system itself and you want to slightly improve the system, the other thing is you can use a simple root locus design as well. So, if you want me to recommend, then I would say that you can use both of them, try to understand the whole system better with the root locus, and then you can even slightly improve with the PID. If you use root locus and combination of PID, you can better design a much better controller. So, the basic is if you understand what needs to be done, then you can directly solve it using any of the techniques. So, that is about a PID controller. So, what we have learned in the PID controller and the root locus, we are mostly satisfying the time domain specifications. So, the most important is a lot of problems, not only time domain, but there can be frequency domain issues as well. So, frequency is as important as time. As I mentioned earlier, a lot of information that we cannot see in time domain, we can see in frequency domain. So, frequency domain complements the time domain. So, what we can see in a frequency domain is we can analyze the system bandwidth and we can know what happens if the input frequency is changed, if the speed of the input is changing, how does the system response. So, this is what we call the frequency response that you can see in the bandwidth. So, you can see for what range of frequencies you can see the system responds with good gain, we can actually analyze from the Bode plot. So, what we can do is when in the frequency domain, if we have a system with a low bandwidth, we can try to add a pole at 0 and then we can modify the root loop. We can modify the frequency response. This is what we call frequency shaping. So, if your system has a low bandwidth, you can actually add a pole or a 0 combination so that you can change the Bode plot. When you draw the Bode plot, you understood that for each pole and 0, you have its own asymptotes. So, adding a pole or adding a 0 will actually modify the frequency domain plot, the Bode plot. So, what we can do is we can analyze its frequency response and also we can slightly increase its bandwidth. So, other important is disturbances. The most important is we can design the system, design the frequency response such that we can reject a disturbance. In many applications, for example, communication systems, noise disturbances, they have particular frequency. There can be like power line noise, you know the power frequency 60 Hz. So, you have harmonics related to power frequency or electromagnetic interference. Most of these disturbances have certain frequency band. So, what we can do is we can make sure that the gain for that specific frequency, suppose this is a disturbance frequency, I can actually model the gain frequency response such that its gain corresponding to that frequency is low. That means, if I get that frequency input, I do not see that in the output. So, we can shape our frequency response even to remove the disturbances. So, that is one major advantage. This can be even done with the Lie-Glad compensators, or we can normally these Lie-Glad compensators are employed to improve the bandwidth. So, improving the bandwidth will actually improve the performance. If you remember, we discussed on the missile system and missile system fin bandwidth. So, most of the time these Lie-Glad compensators are employed in the control of the missile to slightly improve the bandwidth. So, in the finally, what is the main advantage is, if you want to completely improve the system performance in time and frequency domain, we have to design the system, develop the controller in time domain, analyze its performance and also try to further improve in the frequency domain. So, if you do both time domain and frequency domain, both can complement each other. So, we will complement the time domain and can improve the overall performance. See, our major goal is to improve the system performance. So, we can use any technique, whether it is root locus, whether it is PID or it is a frequency domain, it does not matter. The goal is to improve the system performance. So, the more you improve, it is better. So, we can use all these techniques. So, in real world, it is not one technique, but we actually use everything what we learn. So, that some techniques can solve certain problems and some techniques can solve for the problem. So, students, when you actually are going to solve anything, it is about using all the information and all the knowledge to even provide a better controller. So, in that way, frequency domain complements the time domain and then can provide a much better performance for the system. Now, this is about our learning. The next, we move on to the implementation. So, how do we apply all the theory you learn to the real world? The good thing is we have nice design tools where we can design the controller and work on the system performance, improving the system performance before we apply to the real system. So, one of those design environments or design tools is MATLAB and Simulink. This is one of the most popular tools employed in all the universities by many control design firms as well. So, this is like one of the screenshot I took from one of the examples on the MATLAB. So, you have a helicopter here and we have pitch yaw control. So, all the three controls. So, you can have a PID control 1, PID 2, PID 3 controllers and then the feedback loops as well, and this is just nice modeling. These kind of models are very simple to draw. You can draw in 5 minutes, you can develop this model, implement your controller and then solve the problem. So, by doing this, you can test any signal, you can include a step response, ramp, acceleration, all these inputs are available. So, students can freely choose all these blocks just like playing. You can bring all these blocks and then connect it and then complete the modeling. You can just open this block, introduce a transfer function, make a model, all this stuff. So, I have included an extra 1 hour video session outside the required lectures. So, please go through the 1 hour MATLAB video session, so that you can actually learn how to implement all the controllers we learned in the MATLAB. So, if you implement, you will improve your understanding, and you can actually have fun, and also you can learn much better. It is about learning, it is about improve your understanding. So, in this aspect, MATLAB and Simulink provides much better scope for you. So, this is a Simulink, this is a GUI interface in MATLAB. Not only that, MATLAB has nice programming environment. You can write any program, you can actually solve for any problem as well, not only control. Besides that, we have ready-made tools available, some like GUI functions like LTI view, CISO tool. These are all for single input, single output systems, which we worked in our automatic control lecture. So, if you use these two tools, for example, you can use this LTI tool, you can select what response you want to see, and then you can directly give the input, the system, and then you can directly get the response. So, I just selected step, impulse, pole 0 map, etc. So, you can actually get all this in one plot, and you can actually analyze the system. Then this is one type of LTI viewer, and then we have another information tool, I mean GUI tool, that is single input, single output tool. This is very popular because here you can select Bode plot, step response, impulse response. Not only 4 windows, I can select 7, 8 windows, and then try to actually get everything I want. I can actually include this kind of root locus, what you are seeing here, and then we can open loop Bode plot editor. You can add an extra pole, you can shape the loop, you can see the gains here, we can see what is damping ratio, eta, everything. You click on this graph, you can see every information. So, these tools give you much better learning environment. So, this is the Bode plot here, and then you have all this information, gain and phase plots, all this information you can see directly. So, once we write a simple transfer function in MATLAB, we can view everything, means everything you learn in automatic control you can actually implement in the MATLAB environment. So, students, so this is not a difficult one, this is a very easy, and students self learn it. You do not need any special coaching. MATLAB is quite a nice software. It has a simple programming environment and interface. Student can easily learn, means you can use the help and can learn everything. So, if students start implementing that, they will develop the skills very fast, and it can be very helpful to analyze and learn automatic control. So, in that I have included one extra video session, that is 1 hour session on how to actually do some simple stuff, simple programming in MATLAB, and then how do we implement PID controller. I am going to demonstrate how do we solve everything. So, I will also provide you some simple programming files, so the students can install the MATLAB and then try to implement all the controllers, all the problems which we solved during the class. I am going to solve some of the problems. So, this session will be very helpful, so you can watch it anytime you want. So, in this way, the main objective is the learning, as I described in my first lecture, from theory to application. So, this MATLAB environment bridges the gap. This will help you like you are implementing on a real scenario. So, you can actually analyze everything about the system. So, I strongly recommend students to actually work your problems or also solve and implement in the MATLAB. So, that is all about that part, and now about the final exam. So, coming to our final exam, this is the syllabus from the week 7 part 3 steady state to the end. So, this is all the syllabus for your final exam. So, week 15 is your final exam. So, if you see what we learned on steady state analysis about error dynamics, type 1, type 0 systems, and then we learned the design technique and analysis technique, the root locus. So, very important, and then we learned the PID controller, and finally we learned Bode plot and frequency domain analysis. So, all this part is included in your final exam, but actually if you see, this is the distribution of questions. So, coming to final exam, you can have approximately 9 to 10 questions. Each question will have different marks. However, the importance of the topic you can see here. So, 20% of the marks in the final exam will be from steady state, 30% from root locus, 30% from PID controller, and the 20% you can really actually get from Bode plot. So, this will help you for the preparation and make sure you actually prepare everything. So, I will cover almost all the topics from steady state to root locus PID. So, I only have like 4 or 5 topics, but I can actually include everything in the examination. So, please prepare. So, these are very important. So, coming to root locus, students have to draw a nice root locus and mark every point. Okay. So, they do not need to write every step, but have to solve all the required steps. Okay. Solve the required steps and draw a nice root locus and mark every information in the root locus that needs done. So, that is about final exam. I think that the assignment you solved earlier also will further help for your preparation. So, if you are able to solve all the questions in the assignment, I believe your preparation is almost there. So, besides that, if you understand the concepts well, you should be able to answer. So, no specific problems. I will give you problems from anywhere. So, the requirements will be different, the problem will be different. So, go through the problem carefully. So, before you answer, read the problem twice, understand the problem, and then try to solve it. Do not hurry, because every problem can be different. Another thing, only solve what is asked in the problem. Look at read twice and only solve for what is required in the problem. So, that is the best way. Time managing is very important, as I described in the midterm. Please manage your time carefully, then it will not be any problem. And then we reach our end of the lectures. So, I am very thankful to you for choosing this lecture, and that is why I would like to thank you, and I wish you good luck for your final exam. And if you have any queries and questions, please feel free to approach me. You can contact by email or you can visit my office. So finally, I would like to thank you again. This is end of week 14 part 3. Good luck. Thank you. Kamsahamnida.